Chapter 10, energy. We could all use some energy, right? We're just doing little bits of this chapter. We're actually doing the entire chapter today, at least the only parts of it that we're going to deal with, because this is Chem 10, and I'm teaching out of a Chem 3A level book, and so we don't need to learn everything in the book, and we're not going to. But we do need to touch on some topics of energy. What is energy? A scientific definition of energy is the ability to do work or produce heat. And energy is what is needed to oppose natural attractions. So my pen here is attracted to the center of the earth by gravity. And if I oppose gravity by lifting it up, I have done work. Now, this is different than our definition of work in everyday life, where generally work implies being paid for it or being rewarded in some way. When I lift up this pen, I don't get any financial gain from that, but I have done work. So it's opposing natural attractions. The law of conservation of energy is a very important concept. Energy can be converted from one form to another, but it cannot be created or destroyed. So the upshot of that is the total energy content of the universe is constant. You cannot create energy. Anytime that it appears that you are creating energy, something is being overlooked. And when we transform energy from one form to another, we generally lose a significant amount to unuseful forms of energy. What are the different kinds of energy? Well, potential energy is energy due to position or composition. So when I lift up my pen and I hold it above the floor, it has greater potential energy than it does when it's sitting on the table because it is elevated. It has the potential to fall farther, and if I let go, it falls. As it falls, it gains kinetic energy as it moves faster. Kinetic energy is energy due to motion. And that depends on the mass of the object and its velocity. As the pen falls to the floor, its mass doesn't change, but its velocity increases. And so the kinetic energy increases, and then everything comes to a crashing halt when it hits the floor. Where did all that energy go when it hits the floor? It may appear that it's just gone. It had potential energy up here. The potential energy was transformed into kinetic energy as it fell. As it falls, its potential energy becomes lower and lower as it gets closer to the floor. When it hits the floor, all that energy, or at least most of that energy, is dissipated as heat when it collides with the floor. It's not a significant amount of heat that we would be able to notice with our senses, but there is heat generated. When two very large objects collide with a great deal of force, then there is a noticeable amount of heat that's generated. Heat is generally not a useful form of energy. You can't collect it and do anything with it in many situations. Potential energy is also due to composition. The gasoline in your car has a great deal of potential energy, not because it's elevated above the ground, but because there is energy stored in the chemical bonds of the gasoline molecules. And when you burn that gasoline, those bonds are broken and that energy is released. The engine in your car is able to use that energy to move the pistons and turn the axle and move your car. There's also a great deal of heat released. Car engines get hot, don't they, when they run? That's why you need a radiator and radiator fluid, and if that's not working well, then your car overheats, and it's definitely very hot. So we are able to transform some of that potential energy in the gasoline into kinetic energy, the movement of the car, but some of the energy is lost to heat in the engine compartment. Again, kinetic energy is depending on the mass of the object and its velocity. I'll show you this equation, although I don't expect you to remember it or use it for anything. But kinetic energy is 1/2 the mass of the object times the velocity squared. So A larger object moving at the same speed has more kinetic energy. Two objects of the same mass, if one's going faster, it has more kinetic energy. Think maybe about a kindergartner and a linebacker on the Reedley football team. Okay, I have a child who's almost in kindergarten. He's like, I don't know, 45 pounds or so. How much do those linebackers weigh? Like 250, yeah, so a lot more, right? So if you've got the linebacker and Andrew, the 5-year-old, running at you at the same speed, and they run into you, which one is more significant of an impact? That linebacker, right? If he's even just walking, he's going to walk right through you, isn't he? Now, if you've got, well, let's leave the linebackers alone. If you've got Andrew trotting at you at a slow speed and he runs into you, you're like, ugh. But if he runs full blast at you, going much faster, his velocity is higher, he might be able to knock you down. Because he is, I don't know, he's just like this dense little person. And if he's moving fast, you know, if you're prepared for him, you could lean into him. But if he catches you unawares, watch out. But the speed matters, okay? So those are concepts of energy. Here's some pictures of a guy rolling big balls up and down a hill. So here, ball A and ball B. He's holding this ball A, let's call them boulders. Boulder A, this always goes somewhere bad. Boulder A is near the top of the hill, and he's holding on to it so it doesn't roll down. Because if he lets go, what's going to happen? It's going to roll down the hill. It has potential energy. And if he lets go of that and it starts to roll, it's going to increase its velocity. As it goes down the hill, its speed, velocity increases, so its kinetic energy increases, but it's also going down, it's getting closer to the center of the earth, so its potential energy is decreasing. So that's potential energy transforming into kinetic energy. So this boulder has more potential energy than boulder B does. If it rolls down the hill and hits boulder B, it can make B move as well. And it can transfer its kinetic energy to the other one. So you think of billiard balls, and you've got that white cue ball, and you shoot it at, I don't know, the 7 ball. The 7 ball's sitting there stationary. What happens when the cue ball hits it? Most of the kinetic energy is transferred to the number 7 ball. The cue ball then slows way down, right? Because it transferred most of its energy to the other ball, which now starts to move. So as this boulder rolls down the hill, it gains kinetic energy, losing potential energy. It hits the other boulder and transfers a lot of its kinetic energy, not all of it, to this boulder, and this boulder then starts to roll up the hill. Some of that energy as it comes down is lost to frictional heating. There's friction between the boulder and the surface of the hill, regardless of what the surface is. Some hills have more friction than others. If you rolled this down like a metal slide, there would be a lot less friction and the ball would go much faster. If you rolled this down a grassy hill that hasn't been mowed in a while and the grass is really long, the boulder will roll a little slower because there's more friction. When we get that friction, that's where we get heating. Like you know, if you rub your hands together, they get warm. Where does that heat come from? It's friction. You're turning the kinetic energy of moving your hands into friction because you're rubbing them against each other. It doesn't happen if you move your hands back and forth and they're not touching. Then you've just got kinetic energy. When boulder A hits boulder B starts to roll up, but will it roll up as high as boulder A started? No, because some of the energy has been lost. Now, it's still in the universe, but it's just lost to useful purposes, and a lot of it went to that frictional heating. So this rolls down, hits boulder B rolls up less then boulder A started from. So any questions about hills and boulders? This guy looks kind of puzzled, doesn't he? Like, what happened there? These are weird pictures they put in the books. Any questions? So we said that work was blanking. What did we say work was? The ability to do work or produce heat. Energy was the ability to do work or produce heat. What is heat? Heat is the transfer of energy from one thing to another due to temperature differences. So heat always involves energy moving from one thing to another. We know that if you have a cold object next to a hot object, the hot object will transfer some of its thermal energy to the cold object, and they'll end up at the same temperature, right? The hot one will cool down, the cold one will warm up. It never goes the opposite way. Work is a force acting over a distance. A force acting over a distance. So that's, in the pen example, the force is me opposing the force of gravity. I'm applying a force to lift it up, and it's over a distance. If I'm just holding this in a stationary fashion, I'm not doing any work. When it's just sitting on the table, no work is being done. There has to be something going over a distance, a force acting over a distance. So energy, work, and heat are related, and yet there's some important differences. We talk about a state function. This has nothing to do with states of California or even states of matter. But a state function is a property that does not depend in any way on the system's past or future. It only depends on the present state. So a state function can change independently of its pathway. Where it is now is what matters, not how it got there. And energy is a state function. Work and heat are not state functions. Work and heat involve that pathway, how you got there. So let's look at these two ideas. A distance traveled from one location to another. So this is going to be a very sad map. I don't know what's wrong with this. Oh yeah, this is the busted stylus. That's the problem. So here's Reedley, and this is Fresno up here. Fresno City College is about right there, and this is Reedley College. So distance traveled from one location to another. We're trying to decide, is this a state function? Does it depend on the pathway? Well, there's different ways to get to Fresno. You can take Manning Avenue and Highway 99, then you go up, and depending on your preference, you're going to, somewhere in here, you're going to get on McKinley, and you're going to go over to Fresno City College. So there's a distance involved, right? You've got a Google Maps app on your phone. It'll show you these different pathways, different ways to get there, and there's different distances, right? Or we could go up Reed Avenue and take 180 over and then end up at the same place. Is the distance going to be the same? It's going to be different. The distance traveled from one place to another depends on the pathway. Another way you could get from Reedley to Fresno is you could head east and you could go all the way around the planet and come over to Fresno from the west side. That would be a lot farther, wouldn't it? The beginning point and the ending point are the same, though. but the distance traveled is not the same. Distance traveled between two places is not a state function. Does that make sense? Let's talk about change in elevation. So are these state functions? Distance traveled? No. So let's draw another sad map. Okay, so here's Reedley, and up here is Grant Grove, right? And to get to Grant Grove, you can go there different ways. You can go up 180, it's probably the most direct route, or you could go over by Heartland Christian Camp and drive up Whitaker Forest Road. The distance is going to be different, right? The elevation here in Reedley is about 355 feet above sea level, and I think Grant Grove is roughly 6,000, give or take 1,000 feet. It's up there though. The change in elevation between Reedley and Grant Grove, does it matter how I got there? No. It doesn't matter if I drove straight up 180, or if I went over here and came up this way, or if I took a helicopter. If I took a helicopter and I went way up and then came down, my distance traveled would be different, but the change in elevation is the same regardless of pathway. So change in elevation is a state function. Doesn't matter how you got there, your change in elevation is the same. So we need to go back here. So energy is a state function. The energy change does not depend on how it happened. Work and heat are state functions. The amount of work exerted, the amount of heat transferred are state functions. It depends on how it happened. Any questions?